When linking large fact tables to comparatively small dimension tables, table links perform well. But let's say we have to link two large fact tables together. The base table contains 60 billion records, and our foreign table has 15 billion records. At these scales, we can use our understanding of the data to accelerate the linking process. Basic linking can be thought of as a linear scan across columns. Let's use our two large fact tables. Table A is the 60 billion row base table, and Table B is the 15 billion row foreign table. For every record of Table A, we need to compare the record's link key columns with the corresponding values in each record of Table B. If we say the base table has n records and the foreign table has m records, we need to do n times m comparisons to fully resolve the link. In our example, that's 900 quintillion comparisons. 1010 data uses optimizations like comparisons occurring on a segment-by-segment basis in parallel to reduce the number needed. However, this is still a ton of comparisons that take time to compute. Sortseg linking lets the link complete orders of magnitude faster. A link that takes many minutes with a basic link can be done in a fraction of a second with a sortseg link. To use sortseg linking, the foreign table must have the sortseg property for the link key column. To get maximum performance from the sortseg link, the base table also needs to be sortsegged on the same link key column. Let's understand what this means. A table sortsegged on a column has data segments that are globally disjoint, meaning minimum and maximum values of each segment don't overlap. Data segments are also locally sorted with respect to that column. Segmenting a table means all records with identical values are stored together in the same segment. For example, a retail transaction table may be segmented by transaction ID. Let's look at two segments of this table. The first segment contains all records associated with transactions 1, 3, and 5, while the second segment contains all records associated with transactions 2, 4, and 6. The maximum of the first segment is 5, while the minimum of the second segment is 2. While this table is segmented by transaction ID, segments are not globally disjoint. We can move records to make them globally disjoint with respect to transaction ID. Here, we've ensured that the minimum and maximum of each segment don't overlap. We've met the globally disjoint requirement, but aren't sortsegged on the transaction ID. A sortsegged table also has the property of being locally sorted. This means that within each segment, the records are sorted by the key column. Our first segment would have transaction IDs 0 through 3, and our second segment would have transaction IDs 4 through 6. Now that we have a sortseg table, we can be clever. It is not necessary to example every row or segment of the foreign table. Binary search can zero in on the right segment, finding the corresponding match. Binary search algorithms are amazingly effective. Looking back at our 15 billion row foreign table, performing the link could take 15 billion comparisons per record using a traditional linear comparison. Binary search can do the same thing with just over 10 comparisons. By using sortseg linking, we take advantage of the binary searching to get the best possible performance.